Hi everyone, I am Hussein Amouri, a PhD student from the ICUB University in collaboration with IGN for the project IATUS. I'll be today explaining my work in my PhD during the 3 years. So before diving into the problem we are trying to solve, first I'll highlight some introduction because most of you are from geographical backgrounds, so you might not be familiar with the concept of shapelets and time series. So as you all know, a time series is just an ordered sequence of points through time or not. The idea is it should be chronological. And the idea behind shapelets is similar to finding patterns. You try to search for a subsequence from the time series where this subsequence best resembles a part of the time series. So similar to prototype and finding patterns in a time series. So for example, for another time series, this shapelet doesn't resemble any part from the other time series in this time series. So basically, it can differentiate between two different families of time series. So the idea behind shapelet, it should find a subsequence that is discriminative between different time series families. This allows us to do a transformation of the time series into a different space by using these shapelets. So for example, if we have this shapelet and we slide it over the time series, at each instant, we record the distance between the shapelet and the subsequence of the time series, and we record the closest one to it. And this is just basically what a shapelet transform. And this allows us to transform the time series into a different space, which can use different measures beside DTW. So this is basically why we want to use this shapelet transform. And another concept, it is constrained clustering. So basically a clustering is just a grouping of points, while constrained clustering, you try to introduce the expert into the clustering process by providing some kind of constraints. Constraints takes different types. What you are interested in are the instance level constraints. So basically you just provide if two instances should belong to the same cluster, to the same family, or not. And for example, between these two clusters shouldn't belong to the same family. So this is the idea behind constrained clustering. So let's now talk about the problem. Imagine you have this data where the expert wants to cluster 3 cuts in this image. So in unsupervised manner, this will be super hard for the algorithm to do clustering by itself. First, because the 3 cuts are not highly representative in this image. And second, some of the clustering algorithms don't use elastic measures that works with the distortions of time series. So basically, in our work, what we do, we take the image. Each pixel has a spectral signature. We work with the spectral signature of the pixel, so we have the time series. And to do clustering, basically, we use elastic measures because it is one-to-many mapping that allow to take these distortions into account. So another approach is try to include the constraints into the clustering process of the time series. When we add constraints, 2 problems rise. The first one, are the constraints informative? Meaning, if you provide constraints to the algorithm, does these constraints add any information to the bias of the algorithm already, or can the algorithm cluster these 2 points by itself without this information provided by the expert? The second one, are the constraints provided by the experts coherent? Meaning, did he provide any conflicting constraints? Because the expert will just look at this image, for example, and say, this pixel and this pixel are 3 cuts, and this are not 3 cuts, which might be true or might not be true. So to do this, to calculate these 2 measures, we need one, an Euclidean space, and second, if we need an Euclidean space, how we will take into account the distortions of the time series. So we need to take into these 2 parameters into account. To do this, we propose a semi-supervised representational learning for the time series based on the concept of shapelets, while introducing the expert to the learning process of the representation. The introduction of the expert is done through using constraints. So instead of using constraints for the clustering purposes, we use constraints for learning the representation. So basically, the expert will say 2 time series are similar, or 2 time series are dissimilar, and doing so, he will guide the learning of the representation. And the second one, we try to approximate the distance between the time series and the transformed space to that of the DTW distance. So this is the first contribution. So how we do this basically is just by introducing the contrastive loss term. So this is the primary loss function, which just guarantees that the distance between two time series using DTW is approximated in the transformed space, while the second term, if the experts provide a must-link constraints, it guarantees that two time series in the transformed space are pushed together as much as possible, and if two time series are not close to each other, they are not belong to the same cluster, it pushes them further apart from each other. So now I'll provide some results we have. So just this to understand what we will see. So in the x-axis, you will see that our representations with the basic k-means clustering. So, and on the x-axis, you will see the row clustering using COP k-means, which is a constrained version of COP k-means. Basically, it just the experts provides their k-means, constraints, must-link and cannot link, and the algorithm has to satisfy all of these constraints. So if one constraint was validated, the algorithm will fail. It will not return any clustering. And we use as well here DTW as a similarity measure. So the clustering algorithm, k-means, is modified to take into account the distortions of the time series. We did the experiments on different level, on different tests. I'll only show now the transductive test. We also have the inductive test. So what is transductive comparison? Transductive learning is basically when you have all of the data points, you train on all the data points, and then you cluster on all the data points. You don't have any unseen data. And we test for different portions of constraints. So here we have 0% constraints, no prior information at all. We added 5% of information from the data set, 15 and 25. Looking at the 0% information, we didn't add anything. The clustering with CDPS representation is approximate to that of the row time series with DTW averaging. So we can see like there's a try in wins. When we started to add constraints, we started to see that most of the points that were in it like similar to that of the raw data started to increase their clustering score bit by adding more constraints. Hence, the constraints are affecting the space that we are learned toward a better representation for the time series to allow for a better clustering. And in the new space, we have Euclidean distance in the shapelet space. Hence, we can measure the informativeness and the coherence of the constraints further on to see if these constraints are good or not. Now I'll explain the second contribution we did, which is since shapelets by themselves are subsequences of the time series, they can be interpretable by the expert. So the expert can see the trend, can see a cycle, the seasonality of the time series being clustered together. So he can say that, okay, this group have this trend, this cycle, and this group has this trend, this cycle. To do this, we use the information gain, which just a measure to say, okay, after a specific split, if you split the data sets into two groups, is this split good or not? And we propose 3 different approaches: independent, combined, and successive, and we'll say why successive is the most important one. So first, I'll explain again what is the information gain. Suppose we have the points in this space. The information gain, after defining a specific split, tries to measure the entropy in this partition and the entropy in this partition, and just subtracts the entropy before and after the cut, and hence we'll see how pure our clusters are coming. So the first approach is the independent, where we deal with each time series learned independently. So in the process, we are learning like 100 shapelets. So we need to rank these shapelets from the most informative to the least informative for a specific split in the time series. So to a specific split. Here we have, for example, the shapelet 60, where it splits the data points almost good enough. But what happens when we want to stack all of the shapelets together? So we have all the shapelets learned, we rank them. If we follow the independent, will there be a linear dependency between the shapelets stacked together? Because you might learn 2 shapelets that are quite familiar to, similar to each other. Because it's semi-supervised, and we don't say that you like add a constraint to the shapelet learned might be similar or not similar. The second one is to combine shapelets. So instead of working with each shapelet independently, now we say, okay, let's find the first shapelet, and second, we try to find the second shapelet that best add information to the second one as a plane, and so on, building the space by the shapelets learned. Now the most important is this, the successive. And the successive, we want to to measure the information successively add. And combined, the second shapelet added might be similar to the first one, and might not add any information, but still be the most informative along between its peers. While in successive, we try to find the shapelet, the second shapelet that adds information to the first one by measuring the information of the points that changed toward a good partitioning. So it had partitioning A, for example, at the beginning. When we add the second shapelet, it changed from A to B. This is the first point. And the second point, we also take into account the misclassified point, the mispartitioned point as well. So now I'll show you an example on the synthetic control dataset taken from the UCR archive. So we have these different categories. We have two categories that have a downward trend, and two categories that have an upward trend, and two categories that have, let's say, cyclic trend in them. So first, this is just a figure of the shapelets, ranking of the shapelets using successive. We have here almost 50 shapelets, 60 shapelets, and we rank them from the most informative to the least informative. The figure is the normalized cumulative information gain. So here plateau means that most of the shapelets here doesn't add any much information beside the first 10 shapelets found using the successive approach. So here we can see that the first shapelet chosen, it has an upward trend. The first ranked shapelet, it has an upward trend, hence it best differentiate between the upward trend, the green one, and the red one from the two downward trend categories, while the one which is cyclic almost spans over everything because it has both the upward and the downward trend. The second shapelet learned and found using the successive approach is the downward trend, where it tries to separate between these two between the other two families, and finally the last one, which has into account the cyclic trend, and hence in the space all of the points will be separated as much as possible. This will allow to do like similar to PCA, where you can do a limit to how much dimensions you can have, a dimensional tree reduction. You can also, following this approach, you can choose the number of shapelets to stop at. So for example, the blue line is the normalized information gain, while the orange is the NMI with respect to the predicted, to the clustering you want to explain. Okay, this will be there. So, and here you can see if we stop at around 10 shapelets, we can attain the same clustering result when using all of the shapelets. So this is just showing the results by doing this shapelet selection. For example, having one shapelet can attain 77 information of the clustering score. For simples 2 attains 82%. But this, of course, will add a trade-off. Using all the shapelets, you still have the approximation of the DTW, while using less number of shapelets, you will lose the approximation of the DTW. And thank you, that's all.
Thank you very much for the presentation. Y a-t-il des questions dans l'assistance? Oui, Olivier.
Yes, thank you. I'm not sure I understood how you construct your time series, but it seems to me that your approach is basically monoscale, or not really robust to a time series that would be composed of several different signals with different time scales. And so did you try the classical mathematical methods such as wavelet analysis, or I would say any decomposition on an orthogonal basis that would be able to capture maybe a more systematic view of the signal? I understand totally. So it really depends on the kind of information you're trying to capture, but maybe something more, let's say, agnostic could also give interesting results.
So the idea behind using shapelet that they are more, if I understood your question, are explainable. So they have interpretability into them. They learn the same thing. And for if the time series has different length, the shapelet doesn't care about the length of the time series, so it does adapt to it. So the only problem when dealing with shapelets might be if you have gaps in the time series.
It's adaptive, but it's not multi-scale. You capture only one scale with each shapelet.
You can normalize all of the other dimensions, and then you can use the shapelets, or unless the normalization isn't into account the Z normalization, it cannot be done. So yeah, you do it, but you can have also a multi-scale shapelet learning. So in the literature, there's also shapelets that learn different scales for the shapelet. But in our approach, we didn't dive deep into that. We just wanted to highlight on the information added by the expert.